Hi everyone, welcome to another video by Cheenta. I am Rajdeep, and today will be the first video in a series of many where I explore some of the basic ideas of number theory. We'll start from the basics, assuming practically nothing, and hopefully by the end of this series, you'll have developed some comfort and some appreciation for number theory. In this video in particular, we'll start, funnily enough, with the very first problem of the very first IMO. It's a classic problem and it provides a gateway for some of the very early, primitive and very important ideas of number theory. So I hope you enjoy and let's get into it. So this is the problem that we're talking about. This is from IMO 1959 and it's the first problem. Let's see what the problem says. The problem says that prove the fraction 21n plus 4 by 14n plus 3 is irreducible for every natural number n. Let's try to unpack that. What does it mean for a fraction a by b to be irreducible? So, for example, the fraction 10 by 14 is not irreducible. Why? Because 10 and 14 share a common factor. We'll look further into what this means, but we know that 10 is 2 times 5 and 14 is 2 times 7. So we can cancel this 2 out from the numerator and denominator to get that 10 by 14 is 5 by 7. This is what it means for a fraction to be irreducible. It means that the numerator and the denominator share no common factors. So what does the question say? It's saying that no matter what n you choose, this fraction is going to be irreducible. So, you should take a moment to appreciate the scope of the problem. It's saying that every fraction in this sequence, 21 into 1 plus 4 by 14 into 1 plus 3, 21 into 2 plus 4 by 14 into 2 plus 3, and so on. Every single one of these fractions is going to be irreducible. There's something remarkable about that. I would urge you at this point to pause the video and try the problem for yourself. So, you should try it. So hopefully after attempting this problem, you have some appreciation for its difficulty and for its scope and for how far reaching its conclusion is. Now, how do we try to prove something like this? Really, what we are being asked to show is that the greatest common divisor of 21n plus 4 and 14n plus 3 is equal to 1. This is just another way of saying that 21n plus 4 and 14n plus 3 don't share any factors. The greatest common divisor and factor mean the same thing, is just the largest number that divides both of the numbers involved. And if that number is 1, that means that there are no prime factors, right? There's no common factor among them. So we want to prove a statement like this. How would we prove something like this? This is hard. Like, you might have learned some ways of, finding a greatest common divisor in school, and maybe not. Maybe it's been a long time and you've not seen something like that. There are certain things you can do. You can do something like inspection. If I asked you to find the GCD of 12 and 10, you could guess. You would say that, okay, these are both even numbers. So, it's 2 times 6 and 2 times 5, and 6 and 5 don't seem to share any factors. So the GCD must be 2. That was inspection. For those of you who might be familiar with prime numbers and prime factorizations, you could try something like that. That, in my eyes, I don't see a solution using prime factors right away. This will involve something called the Euclidean algorithm, which is the topic of today's video. So the flow will be as follows. This is our main problem that we'll try to solve. To do this, we'll first explore what divisibility is, and then we'll look at the number line. In particular, we look at the Euclid's lemma, after which we'll look at the GCD as a thing of its own. We'll discuss that shortly. Finally, we'll look at what the Euclidean algorithm is, and we'll use that Euclidean algorithm to solve this problem. So let's put this problem aside for a bit and discuss what divisibility is. So I'll make it quick. I'll write that A divides B, and I'll use this notation, or A divides B, to mean what we understand it to mean. To mean that, it's a restatement that B is a multiple of A, or that B is K times A for some. That's exactly what it means. For some integer K. All of this is where A and B are integers. All of number theory in some way is, at least it starts from trying to understand the natural numbers and sort of by a very small extension, the integers. The properties of the integers, the natural numbers, and again by a little bit of an extension, rational numbers. It is in their properties that we get numbers here. It's from them. And we see that there's lots of mysterious patterns among these numbers, and it's why number theory is as arcane as it is. Regardless, so we use this notation, and I'll let you get comfortable with it by giving you some examples. 2 divides 6. 6 is 2 times 3. 5 divides 10. 4 divides 24, and so on. This is what it means to divide. We also say that B is divisible by A, right? A couple of things. If A divides B and A divides C, then A divides B plus C. This is one of the first things that I want you guys to understand. If A divides B and A divides C, then A divides B plus C. Take an example. I want you to not have to think about something like this, just so that it's immediately clear. If B is a multiple of A and C is a multiple of A, if you add two multiples of A, you should get another multiple of A. This it's encapsulated by the idea that multiplication is just repeated addition. B is just A added with itself a certain number of times. C is just A added with itself some other number of times. You put them together, you just get A added with itself a bunch of times. So that's just a multiple of A. Quickly, why is this true? A proof, if you will, is that if B is equal to Ka for some K, and C is equal to La for some L, where K and L are integers, then B plus C is equal to K plus L times A. So B plus C is something times A. Hence B plus C is a multiple of A, or that A divides B plus C. Generally, sort of by a very simple extension, if A divides B and A divides C, then A divides B minus C. Almost the same thing. Instead of K plus L here, you would get K minus L. Another kind of obvious thing is that if A divides B, then A divides any multiple of B, right? If you had that 2 divides 4, obviously 2 will divide a multiple of 4. You can kind of think of it as the same thing as that. If 4 is 2 written twice, added with itself twice, similarly if B is A added with itself, if B is equal to A plus A plus A a certain number of times, multiplying B by something is just adding A with itself more number of times. So at the end of the day, it's just A added with itself a bunch of times, and hence it's a multiple of A. This one's kind of obvious. A multiple of a multiple is a multiple. And so what this tells us is that you can kind of do the basic operations across the divide sign. So in particular, generally speaking, if A divides B and A divides C, then A divides Bx Cy for any integers x and y. You can take any linear combination of B and C and get that A divides Bx plus C, Cy. Let me give you a quick problem to solve here so that you can get comfortable with something like this. This is a very classic and very simple problem from Olympiad number theory, which is find all natural numbers n such that n plus 1 divides n square plus 1. Okay? It's a sort of a similar kind of problem as our goal problem, right? It's trying to make a statement of divisibility which is parameterized by all the natural numbers. So, can 3 divide 2 square plus 1, which is 5? No. And so on. So you kind of answer a general question about n. So again, I urge you to pause the video at this point, try it for yourselves. Right. So hopefully after your attempt, you have some appreciation for what the question is trying to say. In this case, what I can do is that if n plus 1 divides n square plus 1 and n plus 1 divides n square minus 1, you might see, where does this come from? This comes from the basic algebraic fact that n square minus 1 is n plus 1 times n minus 1. Right? A square plus minus b square is equal to a plus b times a minus b. So n square minus 1 is n plus 1 times something. That's the idea of divisibility. A divides b if b is a times something. That something is irrelevant in the context of divisibility. So since n square minus 1 is n plus 1 times something, n plus 1 divides n square minus 1. For all natural numbers n. This is true for all natural numbers. This is true all the time. So I use this fact. Since if n plus 1 were to divide n square plus 1, and since n plus 1 divides n square minus 1 all the time, whenever the first statement is true, I can use both of those to imply that n plus 1 divides n square plus 1 minus n square minus 1, which is what? If n plus 1 were to divide n square plus 1, then n plus 1 would have to divide this thing, which implies that n plus 1 divides 2. Very few things divide 2. From here, I'll assign that as homework, if you will, to see which numbers can n be. N plus 1 has very few choices. N plus 1 can either be 1, plus minus 1, or plus minus 2. So there's 4 numbers which do this job. Right? Coming back to our setup, what's the next thing we want to discuss? Euclid's lemma. We'll use the number line as a sort of utensil for holding what's called the well-ordering principle. I won't go into what that is. You can look that up for yourselves. But I'll use the number line as a utensil in that sense. Think about what the multiples of a given number A look like. On the number line, you have any number, divide 0 because anything times 0 is 0. You have 0, the number A, the number 2A, then 3A, then 4A, and the other side you have minus A, minus 2A, and so on. For, if you take the example of 2, you have 0, 2, 4, 6, minus 2, minus 4, and so on. So I kind of look at these multiples of 2 on the number line. There's all sorts of numbers here. For now, we only restrict our attention to natural numbers. So there's 1 here, and 3 here, and 5 here. But we only look at 0, 2, 4, 6 for now. If I want to locate another natural number B with these multiples of A as landmarks, I could do that. That is the point. That if I choose any other number B, say B is here, then B can be approximated, if you will, by a multiple of A. We can always look for the largest multiple of A in the positive side, smaller than B. So in this case, B is equal to A plus something that's less than A. think about taking steps of length A along the number line. Then you will find the in between two of your steps, no matter what A is. So, if I take the example of 3 rather than 2 to make things clear, you have 0, 3, 6, 9, this direction, -3, -6, -9, so on. We have 1, 2, 4, 5, and so on. If I ask where's 10, I can say 10 is 1 plus the third multiple of 3. I hope you understand what I'm trying to say here. So I can consider any number and locate it with respect to the multiples of A. So this is what brings us to the division lemma, sometimes known as Euclid's division lemma. What that says is that given any integers B, A and B, given any integers A and B, you can say that there are integers Q and R such that B is equal to AQ plus R. I'm not doing anything new here. What I do here is I look at all the multiples of A, 2A, and so on, and I see where B lands in between or at a multiple of A. And I simply say, oh, go to this multiple of A and then walk the rest, if you want to think of it like that. Where I can say that R is between 0 and A. It's definitely less than A, right? Because, you can always say, oh, okay, 10 is equal to, 3 into 2, which is 6 plus 4. But that's not the closest multiple of 3. So I can always go to the closest multiple of 3 and then only walk a distance less than 3. So I can do this for any integer. That's what I'm doing. So I think of the number line in terms of these landmarks, which are multiples of A. And so R is called the remainder and Q is called the quotient. That's what the division lemma says. It's a very simple idea. Now, why do all this? Remember that the problem that we were trying to solve asks us about the GCD. Let's do that. What is the GCD? The greatest common divisor. Some of you might know this by the name of the highest common factor, the HCF. Same thing. What is the GCD? Let's first get the notion of the common divisor. If A and B are two integers, then a common divisor D is an integer such that, understandably, D divides A and D divides B. It's a common divisor. It divides both A and B. Among all the common divisors of A and B, the largest one is called the GCD. So if we take the example again of say 12 and 10, what are all the divisors of 12? We only consider positive divisor when we ask this kind of a question. The negative divisors are kind of hidden. It's mostly a matter of convenience. So there's 1, there's 2, 2 divides 12, right? 2 times 6. Then we have 3, we have 4, we have, not 5, we have 6, we don't have 7, we don't have 8, we don't have 9, we don't have anything right up until 12 itself. 12 obviously divides itself. For 10, we have 1, 2, not 3, not 4, but 5, and then 10. And so, what is the greatest common divisor? In fact, in this case, there's only one common divisor, which is 2. So, 2 is the GCD. We write this as GCD 12 and 10 is equal to 2. So this is a strategy of finding out what the greatest common divisor is. List out each of the divisors and just see which is the largest common one. That's our strategy. Clearly for us, that's not going to work. To solve our original problem, this will not work. Mostly because after a certain point, you can't even the numbers are far too large to sit and find all the divisors of. It takes forever. And also, we want to prove a statement for all n. There's infinitely many natural numbers. This brings us to the following important idea. GCD of A and B is equal to the GCD of A and B minus A. If you remember the fact that if D divides A and D divides B, then D divides A plus B and D divides A minus B, this shouldn't come as too much of a surprise. If D divides A and D divides B, which the GCD does do, it will also divide B minus A. So every common divisor of A and B is a common divisor of A and B minus A, and vice versa. If a certain number divides A and a certain number and the same number divides B minus A, it will also divide their sum, which is B. So there's this clear correspondence between common divisors of A and B and common divisors of A and B minus A. So obviously, the GCD is going to be the same. You can take some time and get used to this idea, but it's not too hard to believe. Hopefully, after our tryst with the algebra of division. Why is this a useful idea? That if I start with two positive numbers, in this case 12 and 10, I can reduce one of the numbers, right? GCD of 12 and 10 is the GCD of 2 and 10, because 2 is 12 minus 10. So whenever I have two positive numbers, making sure that the numbers stay positive, I can keep subtracting away the smaller number from the larger one. And this process is bound to stop because we fix our numbers to always stay positive. So we keep doing this process until at a certain point, we'll get that one of the numbers divides the other. This is the Euclidean algorithm. And so in this case, it's clear. GCD of 12 and 10 is equal to GCD of 12 minus 10, 10, which is the GCD of 2 and 10, which is just 2, because 2 divides 10. You can keep doing this, and the idea is that the process will stop, because the numbers are positive, and we want them to stay positive. You can't keep reducing numbers while they're positive. This is an idea that's also a sort of great philosophy of its own. It's called monovariance, and it's used a lot in combinatorics and so on, but that's for another time. We can use this to our advantage. Whenever you want to calculate the GCD of two large numbers, you can keep performing this subtraction thing until your numbers are too small or it's obvious that what the GCD is. We can take a different example. GCD of 24 and 13. The GCD of 24 and 13, using our idea, is the GCD of 11 and 13, which is 24 minus 13, which itself is, now we go the other way. 11 is less than 13, so I use 11 and 13 minus 11, which is 2. I can see that these are two obviously co-prime numbers. 2 and 11 are obviously going to be co-prime because 11 is odd, so this is 1. So we formalize this at once and say that the Euclidean algorithm does this thing where it starts with two numbers A and B and reduces A from B as many times as possible as long as the two numbers stay positive. How many times can we do this? If you look at the division algorithm, it gives us that exact answer. How many times, so if B is here, how many times can you subtract A from it? Right up until this Q. So if you take away A from B Q times, you're left with a number that's less than A, and you can no longer take A away. So you reverse the process. In particular, GCD of A and B is equal to the GCD of A and B minus QA. We do that process Q times to get that this is the GCD of A and R, right? And now where R is less than A, still positive by the way, via the division lemma. Now we repeat the process. Eventually this process will stop and we'll get our GCD. There's a more formal way of stating this, which I'll not get into. I will immediately use this to solve my problem. We want to find the GCD of 21n plus 4 and 14n plus 3. In fact, we want to show that it's 1. So what is 21n plus 4 minus 14n plus 3? That is equal to 7n plus 1. So the GCD of 21n plus 4 and 14n plus 3 is equal to the GCD of 7n plus 1 and 14n plus 3. I do the same thing again to get that the GCD of 7n plus 1 and 14n plus 3 is 7n plus 1 and 7n plus 2. I subtracted from 14n plus 3 7n plus 1. And now we are done because the GCD of 7n plus 1 and 7n plus 2 is the GCD of 7n plus 1 and 7n plus 2 minus 7n plus 1, which is just 1. So this is the GCD of 1 and any number is obviously 1. And we're done. So very quickly, I gave you an introduction to divisibility, to Euclidean lemma and the Euclidean algorithm to solve this classic IMO problem. And I hope you enjoyed that. And obviously, I would urge you to do some background reading. There's lots of material online. There's lots of great Cheenta videos. The Cheenta course itself is incredible for something like this. So now the onus is on you to figure out more about this theory. But I'll return with another video on number theory and explore a slightly advanced concept. Hope you had fun. Bye-bye.